One last application of work that we need to deal with is what happens when you have some sort of a plate, and we usually make it a reasonably nice geometrical shape. A trapezoid is slightly difficult, but not too difficult, so that one's a common one. And this lies underwater, or at the very least is being pressured by a liquid from one side and not from the other. And what we want to know is just how much pressure is on this. And the idea is that pressure depends on depth. And so the pressure at any point along this line, the force at any point along this line is the same. And so what we want to do is to orient ourselves vertically and to say, all right, let's say that we have this trapezoid that at the base is 4 meters, at the height is, or at the top is 6, and let's say that its total height is 2 meters. Then we can take over here y is equal to 0 as our base, and we can say that the total amount of pressure on it builds from y is equal to 0 up to y is equal to 2. And what we find is that the so from the lowest point to the highest point, let's do this as generally as we can. So from the lowest to the highest, and the pressure, the force is rho times g as usual, right? It's going to depend on just how dense the liquid is. If we have something that is being pushed by water versus something which is being pushed by liquid mercury, it's going to have a difference on the amount of force that's involved. Whether we do this here or on the moon is going to make a difference, so that gives you gravity. And then we need the depth of the liquid, and we need the width of this line, the width of contact, might be a nice way to look at it, dy. And that's it. This is the entire idea. By the time you're done with the emptying and filling of tanks, this application is trivial. This one becomes very straightforward because all we need is to look at this and say, all right, we have a trapezoid. Here's 4, here's 6, and let's look at the perpendicular right here. This is going to be 2. So if I am at a height of h, then I can figure out this little triangle using similar triangles. Notice how many times we've used similar triangles already. It is incredibly common. This is 2. What's going to be the overhang? If I look at these verticals, that's 4, so that's 1, and that's 1. So this is 2, this is 1, this right here is h, and this over here is some extra, let's call it x. So x is to h what 1 is to 2, so x is equal to h over 2. Therefore, the width is equal to 4 plus this overhang on the right, and the same on the left, gives us simply 4 plus h. And let's say that we are sitting under 2 meters of water. So what we have is an integral from 0 to 2 of rho times g times your depth. You write here the depth of h, and at the very top you're at y is equal to 4. So the depth goes from 4 down to h itself. The width is 4 plus h, and by this point we've moved to h as our variable. H and y are the same, right? They're both starting at 0, so it's very common for that to happen. When it happens, you'll see that you can just interchange h and y. When you have your y starting somewhere else, like here or at water level, it will not be simply interchanging them and doing examples where you have them meet up versus examples where you don't is going to force you to see the differences, to see where you can just use h's and where you're playing around with h's and y's that are a little bit different from each other. And so this is rho times g, integral from 0 to 2 of 16 minus h squared dh, is rho times g, 16h minus h cubed over 3 from 0 to 2, is equal to whatever it is that it's equal to. 96 minus 8 is about 88, so 88 rho g over 3. And whatever units you use for all of these, make sure that they're consistent. So since we're using meters, make sure that your values, not just for gravity, but also for density, that they use meters as well, and you will end up with a value for work.